system is a connection by which a steady flow of current goes to ground. In other words, if we don't have current, we don't have a ground. And we don't want that path of least resistance to be through somebody or through us or some delicate piece of equipment. We want it to be through a ground electrode system. Now, a lot of times you won't have much current, so an ammeter that is not sensitive enough, in other words, it doesn't measure down to milliamps, might not indicate that there is a current flow when in reality there is. And let me add that for safety's sake, and different companies use different specs for this, so I'll use the most stringent. If you find you have more than 2 amps of current, you likely have some kind of a ground fault that makes it unsafe. So, the benefits of proper grounding. Well, certainly not in order of importance, but in chronological order. The 3 P's development of grounding was like this. Sort of for millennia, people noticed the power of lightning. I mean, I remember vividly when lightning literally blew up a poplar tree in my front yard. And when buildings eventually became taller than the natural things that surrounded them, these buildings were occasionally struck by lightning. Now, before the properties of electricity became understood, lightning was viewed as an act of God, and the only protection was thought to be afforded by prayer. Experiments by Benjamin Franklin and others resulted in his invention in 1749 of the lightning rod ground system to dissipate this lightning. Now, as we came to understand electricity more, and then with the advent of commercial electricity, the need developed to protect people from its more dangerous properties, and grounding became a part of this protection. We've had telephones since the 1870s, but commercial electricity only since the 1890s. And with the advent of commercial electricity, we learned that bad grounds led to a hum on our communication circuits. But, you know, for most part, we could live with that. And now we know that bad grounding leads to noise on our high-speed data circuits in Telco and CATV. This is a little harder to live with, but we could. Now we have to worry about impulse noise. We now have data services that are digital, bits or pluses and minus voltages that are impacted by noise. Now, this isn't a noise mitigation course, but a review of a couple of points is in order. These digital services can overcome steady-state noise like that hum we talked about. Impulse noise always comes from outside the cable. It's always a sign of bad bonding and grounding. If the cables were bonded and grounded, that impulse noise would go to ground and not interfere with the transmitted signals. So mitigation of impulse noise means providing good bonding and grounding. Now, we're not going to go into it here any more than to just say that as data rates increase, the same length of impulse noise spike now knocks out more data bits. In addition, architectures and compression protocols allow each of these bits to carry more information, more data. So the same length impulse noise spike now knocks out more data, more bits and more data. A double whammy, sort of, if you will. Proper grounds are important to move electricity to places where it's harmless. This electricity ranges from lightning with mega voltages like 300,000 amps and 1 billion volts to the microvoltages of a small static charge. And as we said earlier, we used to worry about merely protecting us because we were the most delicate parts of the circuit. Now, it's likely that a piece of electronic equipment is the most delicate part of a comm circuit. And proper grounds also protect us from carelessness, ignorance, and stupidity. But to quote Ron White, you can't fix stupid, so we had better protect ourselves from it. So what exactly is ground resistance? Well, we defined a ground earlier. Now we have to define ground resistance. It's the opposition to current flow of an installed electrode system. When we measure the goodness of a ground, we measure its resistance. We want to know how hard it is for current to get to ground, for it to be safely dissipated through our ground system. We're usually measuring to see if the ground resistance meets some specification. And here are a whole bunch of ground resistance specifications. The point's not the specifications themselves, but rather that ground specifications are all over the board. And as we discussed earlier, grounding has become more important, and some techs are very new at testing grounds, at measuring ground resistance. So they test to a spec that they may not understand. But if anyone knows any ground resistance spec, it always seems to be 25 ohms. 25 ohm ground. That's the goal, was the goal. Why is that? Well, it's because a 25 ohm ground keeps us safe. NEC and IEEE specifications for grounds is 25 ohms. This is the origin of that application of the phrase 25 ohms or less. So stray electricity will find its way to ground. We mentioned earlier that we wanted it to be through a ground circuit rather than through us. Well, if we want the ground circuit, as opposed to us, to be the circuit of least resistance, we need a ground resistance of something less than 25 ohms. Now, that 25 ohm standard has been around for a long time and is what protects us. So since then, tougher standards are sometimes in place because, as I keep mentioning, nowadays we are not the most delicate part of the circuit. So before I go further, we talk about testing. I need to say that you need to use a test instrument designed for ground testing. Now, I'm not going to go into why each of these will not do the job. The Megger books that I mentioned earlier do tell you why you need to use a dedicated ground tester. So in case you're tempted to use something else, don't do that. And it's not within the scope of what we're here to teach safety. However, to be safe working around hazardous voltages, techs need training to understand and maintain awareness of the dangers that they're going to confront. And for that training to be effective, they need the right tools to detect hazardous voltages. These hazardous voltages behave differently from household levels that we're most familiar with. Now, because they do behave differently, they present unique hazards. And technician tools have been designed for that job. So these are just examples of such tools that are designed to check for foreign voltages. Now that we've defined it and we've got where we're going, there are all kinds of situations where we need to measure the resistance of a ground. Someone may want to measure the ground in the second basement of the Empire State Building, or of a large substation in the shadow of a power plant, or, well, you get the picture. There are all kinds of grounds to measure. There are also different test methods to measure these. Most of these test methods are time-consuming. But in reality, a lot of the grounds, especially the ones we're working with, are simple grounds with an existing return paths that that we can test. These can be measured with an easy-to-use clamp-around ground tester. But, as I mentioned at the beginning, clamp testing is so easy that it is easy to misuse or to do it incorrectly. So this is a clamp-around ground tester. Now here's the formula. And I said I'm only going to have one. Well, this is it. This is Ohm's law. And all ground testers use Ohm's law, and the clamp type is no different. We may state Ohm's law in any of several ways, but for our purposes here, just understand that if we know the voltage and current in a circuit, we can find the resistance of that circuit. So that's what these test sets do. They create a circuit where they measure the voltage and the current, and then they calculate the resistance. Well, how do they do that? Well, if you open the jaws of the clamp-on tester, you'll see the ends of two coils. These coils use Ohm's law to calculate resistance. The instrument applies a known voltage to a complete circuit through one coil, measures the resulting current with the other, and then just calculates the resistance. Now there is a proviso. I said that the clamp-on method won't work for all grounds, and if you want to use the clamp-on method, the ground under test must be connected to another ground. It can't be isolated. There must be a circuit, and we're going to talk more about that later. Now, as we mentioned in the early part of this presentation, a clamp ammeter measures current, and if it's sensitive enough, will tell you whether you have a ground. It will not tell you or in any way indicate what the resistance value of that ground is. It won't tell you if the ground is good enough or it meets the specification. The amount of current flowing has no relation to the resistance value of the ground. Clamp ground testers, on the other hand, do measure the current. So they tell us if there is a ground, as well as the resistance of that ground in ohms. Now, it might seem unnecessary if the tester measures the resistance of the ground for it to tell us if there is a ground. But for two reasons, we need to be able to measure current. The first is for safety. There may be so much current that we need to take extra safety precautions. And the second we'll talk about later, but sometimes the set may sort of trick us into thinking that we have a ground when we don't. And remember, if you have a current flow where you're testing with an ammeter, you have a ground of unknown resistance, and you still might be a better ground than the one you're measuring. That's not a good thing. So, this is the first of those three considerations. The clamp-on method, I said, seems easy to use, and we've got to remember these three conditions before we're going to do it. And as I said earlier, we're going to have diagrams and photos to illustrate these. The first is, it's effective only in situations with multiple grounds in parallel, such as pole grounds. Now, this is an illustration of a good application for ground testing. There are multiple ground paths in parallel. So if I put the clamp-on tester around this and it sends out its voltage, there are all of these return paths, almost infinite number of return paths for it to go back. So it's effective in situations with multiple grounds in parallel. We've met it here. This is the kind of thing that we need to do, we need to have to do that. Multiple grounds in parallel. Okay. This is the second of the three conditions. It requires a good return path, so it can't be used on isolated grounds. An example of that is This is just a ground rod stuck in the ground. When the one coil induces voltage onto the circuit, there's nowhere for it to go. There isn't a circuit. So you have to have a circuit for it to get path. You have to have a return path. Now, there are workarounds for this kind of a situation where you're looking, for instance, at a ground rod in a greenfield application. And those workarounds are also covered in the Megger booklets that I mentioned. Now, this is the third one. We said that I'm going to read this, and then we're going to go back and forth a couple of times because you may not be able to follow it the first time. But it says it cannot be used in an alternate lower resistance return path not involving the soil. It has to have a path involving the soil. So this is a diagram of a building with lightning rods here at the corners. And these lightning rods are connected by a wire at the top of the building. Each one is also connected to a ground rod at the corner of the buildings there. So if we clamp around the wire that runs around the roof, say right here, we clamp around this wire that runs around the roof, what happens? Well, as we saw, one coil of the set induces electricity, voltage, onto the wire. The electricity seeks the path of least resistance back to the set where the current is measured. The path of least resistance is this metal wire. So what if, and it doesn't involve the soil. We're simply measuring continuity of the wire. We'll get a reading of a couple of ohms or so, which leads to a rule when using clamp-on testing, sort of a rule. It's my made-up rule, but I'm sure you heard it in several other things. If the reading seems to be too good to be true, it probably is. If we measure this thing anywhere below the lightning rods, like right here where it's illustrated, if we measure it there, the only way that the electricity can get back to the set is through the soil. Like the path of least resistance is probably something like this. So that's the path of least resistance. So let's read this again. The clamp-on method cannot be used if an alternate lower resistance return path exists not involving the soil. This is an alternate lower resistance return path not involving the soil. So we have some examples of these kind of things. This is a telco application. If we clamp where the test set is shown right here, the return path is down the wire to the rods, through the soil, to some other ground rod down here or something like that, and back along the power company ground. It is a return path that involves the soil. If we clamp above the point indicated with the black arrow there, the path of least resistance changes, and it's now metallic. It goes to the power company ground, to the next appearance, down the strand, down the ground wire here, to the tester. So all we would be measuring would be metallic continuity. So to test the resistance of only one of these rods, by the way, you'd have to dig a hole and put your clamp around it here. My point in drawing it this way is a lot of ground systems are comprised of multiple rods, multiple ground electrodes, and as long as you get above them and below where you're hooking to these other grounds, you're fine. A similar example, it was cable TV, and it's just showing, instead of a NID, a coax with a splice here. So it's still the similar type of application. We need to clamp around here and not above that, so that we have dirt in our example. Now, the diagram in the previous slide makes it look sort of cut and dried to decide where to measure the ground. However, when you get out in the real world, it's not always that cut and dried. These pictures of a 1920 car dealership in Montana at different places on that building show what happens over the years as buildings and lots are modified and communication services are changed and wires are added and deleted. And oh, by the way, what's under the concrete here? So with all the weathering of the connectors and insulation in the form of paint being added at the connection, even a metallic continuity can have a resistance that makes it look like a ground. Remember my unwritten Ed's rule: if it seems too good to be true, it probably is. Well, what I'm saying here is even a continuity resistance would be bad. So we wanted to try and measure the resistance, so we pulled the wire back a little bit there. And we measured and got a resistance of 8 ohms. Now, that's either really good ground or bad connectivity. So which was it? What do we do to tell whether it's a good ground or bad connectivity? Well, we just measured the current. That's one of the things our test set does. So we measured the current, and there wasn't any. So it's bad connectivity. Somewhere, lots of paint, lots of corrosion, that kind of stuff. And by the way, what I just described to you is a likely safety violation, because you're supposed to measure the current first for safety, right? Now, this is a butt ground. A butt ground is a wire that run down the pole from the strand ground and attached to a copper plate or coil of copper wire under the butt of the pole. Now, I'm not going to discuss the pros and cons of butt grounds, but rather I am going to say that they're notorious for not meeting the spec with only the first wire installed. So they're often augmented with another rod, as is shown here in this example. Again, we're not going to discuss ways to make that augmentation better. We're just concerned with measuring the various grounds associated with this butt ground. Now, the thing that we would probably really want to do is measure the effectiveness, the resistance of the combined resistance of the ground rod as well as the butt ground. To do that, we clamp around where the red arrow indicates. That way the voltage goes down here. Both of these goes to the next pole, up the pole, the ground wire on that, the next pole that has a ground wire, and down across the strand and down again. So there's dirt involved. We measure the resistance of both of these grounds together. That's the path of least resistance. If we want to measure the resistance of only the butt ground, well, we would clamp around where the green arrow indicates. That way, this is the only thing, the only ground rod that's in our circuit as it goes down to the next ground wire, up to the strand and back down. To measure the resistance of only the ground rod, which is something we might want to do, you could clamp around that rod or wire where the blue arrow indicates. Now, if it was correctly installed, however, it's buried such that the top is about 12 inches below ground. So it's likely to be hard to find anyway. This is another example of why where to measure is vital to getting a good measurement of ground resistance. This tower has 4 ground rods, one at each leg. And the tops of the ground rods are below ground level. They're connected by a buried wire. This wire is connected to each leg of the tower by another wire. That's what I'm trying to illustrate here. If we measure around that last mentioned wire, this thing where it's illustrated, we're only measuring the continuity of the wire connecting the rods. That's probably the path of least resistance back to the set. In other words, this wire here. As we mentioned earlier, there are other methods for measuring the resistance of this ground. But in order to measure the resistance of even one of the ground rods with a clamp around set, we need to dig a hole, put the clamp around each rod below where it hooks on to that wire. We could also cut the wire in various places and so forth. In other words, this situation is not a good application for clamp around ground testing. And here's what it looks like in the real world. This is an actual cell site. Several carriers have equipment here. Now the tower leg is visible in the right side of the left picture here. The ground connections to the ground, are in the right picture right there. If we clamp around any of these grounds, we're going to see current that is very, very low resistance. This is the resistance of the metal and not of the ground. So while there are methods, as I mentioned in the last slide, while there are testing methods to measure the resistance of this ground, it is also not a candidate for clamp-on testing. So what is a candidate for clamp-on testing? Well, this is the diagram of a proper way to measure ground resistance at a pedestal. The path of least resistance is through the ground wire and through the soil to the next ground and back along the cable shield. Now, if we clamped around either one of these cables, the path of least resistance is along the metallic shield of that cable to the next pedestal and back. Therefore, we're not measuring ground resistance. We're measuring the integrity of the shield. So here's what something like that might look like. These photos are of the same cabinet, just from different angles. The rod right here was driven, and then the concrete was poured. Now notice the corrosion there at the white arrow. So how deep does the corrosion go? Well, for that matter, how deep does the rod go? You can't physically get a clamp around the rod at the white arrow, and because of some things that I've said earlier, you might think that doesn't matter. But you can measure the ground resistance by clamping around the wire at the yellow arrow. Now, this is this. This is the ground rod. This is the ground rod. This wire is this wire. It doesn't attach to the rest of the world's grounds until here. So as long as I measure below that point, I can measure ground resistance. In this case, the ground resistance was 88 ohms in an area where grounds were measuring about 20 ohms. So the rod's likely good, but perhaps not long enough. Corrosion was evident in the cabinet, but if there is corrosion at the connectors, well, removing it would improve the ground resistance, but by an unknown amount. In other words, when they put that concrete in there, they did not do us any favors, but we can measure the resistance of the ground. Now, these are two pictures of the same large CATV pedestal. The ground rod is at the center of the smaller picture where the arrow is, right there where that red arrow is. And the best place to measure the ground resistance would be to clamp around the rod where that arrow indicates there, or around the wire. Now the larger picture, this one is taken from the other side of the pedestal. In other words, the ground rod is not visible, but is down here. So the ground wire coming up is connected to wire that goes along this frame where the yellow areas are. That frame is made out of metal, by the way. So if we clamp that wire between the yellow areas, the path of least resistance is along the frame, just like that, and does not involve the soil. Another way to use this in our advantage, this shows what we experience with racks and shelves in a central office or a hub or a head end, where we're clamping there. We're not measuring the ground, but rather continuity. So the path of least resistance is the metallic loops as diagrammed here. Now, while it does not measure the resistance of the ground, it is useful in that this is the method we use to measure the balance of the various ground runs. Depending on the length of the shelves, the heights of the racks, and so forth, this should yield a very low, less than 2 ohms or so, continuity resistance reading. And if it doesn't, there are problems with the bonds along that path. So that's just a measurement of continuity where we make that third law, that third condition work for us. This is a ground handhold. We can easily test the resistance of the ground rod by clamping around the rod below where the wire is welded on, as indicated by this arrow. Now, wouldn't it be nice if all handholds looked like that? Okay, what are we going to do now? We can't get a clamp around ground tester around the rod. Now, perhaps we can get a small ammeter that measures in milliamps around it just to see if there's a ground at all, or whether we have a ground fault. The connector is mechanical, so we could disconnect it and use another method, stake type testing, but the bonding is welded or compression type, we're out of luck. So sometimes it's just very difficult to test, but it could be worse. Now, this is a fanciful illustration to point out that it could be worse. There could be no access. So imagine a remote cabinet with a ground wire from that cabinet disappearing into the dirt underneath it. So we clamp around the wire and get a reading of 0.5 ohm. Right now, by this time in the class, you ought to know that you don't have a 0.5 ohm ground. You are measuring continuity. There's a wire loop down there or something, and the metallic resistance of it is 0.5 ohm. So we have to dig around, find the ground system if we want to measure it with a clamp around tester. Or we could use one of the other more time-consuming methods. There is a way to measure this ground, but a clamp-on isn't the way to do it. So let's do just a quick review. Grounding protects people, property, and performance, and lately, performance has been affected by impulse noise, which is always a sign of bad bonding and grounding. So if you don't know a spec, if you don't know what spec you need to test to, just remember the sort of universal spec. 25 ohms is at least going to protect you. And if you happen to be at a piece of delicate equipment, it probably needs to be better. The considerations we talked about when using a clamp-on tester. It's effective only in situations with multiple grounds in parallel, like pole lines or where you can connect to the multi-ground neutral of the power company. requires a good return path. So it can't be used on isolated grounds. It has to have a circuit. And the one that's most vexing sometimes, that
did we lose you,
voltage
Ed?
that's in.
Oh, I think you went out for a little bit for some reason, but you're
Oh,
back. All
sorry
good.
about that. Well, I was
No
just
worries.
I'm right down to the last one almost. If the measured resistance seems to be too good to be true, it probably is. And okay, Janice, I think we're ready for questions.
Excellent. Well, this is great, and I love all the visuals you shared. Thank you so much. I'm really a visual learner, so I think there are a couple of people out there like me, so I appreciate all that. And, talking slowly and going through this, it's a lot of great information. So I say thank you for all of us. And I will start with the Q&A, and please go ahead and enter those for us now. But we'll go ahead and begin with let's see here, this one. How about the permissible maximum resistance value of MOV arrestor grounding? Arrestor, sorry, my glasses. I need a bigger print there. Grounding in distribution overhead lines.
I don't know. I mean, I can't pull it off the top of my head, but I'll find that. That's easy to do.
Yeah,
so
we've
I'll
got
have
the
to
email.
Say I don't know. Yeah.
No problem. That is fine. We'll get back to you on that one. Thanks for asking. And another one here is, does ground resistance is enough for protecting equipment and people? And why not measuring impedance?
Impedance. Okay.
Impedance.
Yeah, we're just resistance. You use resistance. Resistance is, I should have said in my definition that ground resistance is the opposition to current flow at a frequency, and impedance is the opposition to current flow at in other words, DC is what we're talking about usually with resistance, and impedance is at a frequency something other than that. If you have, I don't know, high frequency transmitters or something that you are worried about. In other words, the ground resistance does change, but we are more talking here about just the way this particular way any clamp-on ground tester works. It's much more complicated to measure impedance. In other words, if you're concerned about different frequencies, and in this part of comms where we're just using a clamp-on tester, we are not. But yeah, you could measure impedance, and I was talking about test methods that take a lot of time. This type of ground test measurements, once you figure out where to put the thing, is like a 2-second proposition. So I remember when I started with the telephone company, we used stake-type testers to measure the grounds of our pole lines, and every 5th pole, you just disconnect stuff, and then you run the stakes out, and it was like, once we got it down, it was like a half hour at a time. This makes it so much easier. So that's what we're worried about here. That's what I'm worried about here, is just simple stake-type resistance thing.
Okay, great. Thank you. You can tell I am not an expert in this specialty that you serve, okay, because I am not even pronouncing these words correctly. So I apologize. But
I tell you what, this is some of this stuff, Janice, is so arcane. I mean, it's a subspecialty of a subspecialty almost.
Yeah, it is. You're right. So that's why we're glad that you shared. Because
when I was at the phone company, the guys that were the noise mitigation specialists, they were like something out of Harry Potter. They were wizards. We're
Yeah.
not sure what they did, but we think it involved spells and wands.
That's hilarious. I love that. I could imagine that back then. That's great. Okay, we have a couple more here. So, and again, help me out if I'm misspeaking, but I'm going to go with this one here. Besides the NID or cabinets being grounded, should other locations like splice closure locations above ground or vault, should splice closures be grounded if the location is shared with other active telco or CATV amplifier locations?
You probably just want to bond. Yeah, you probably, if there's a bond you can ground to, you just want to do that. You don't want to take the chance of being the best ground. That sometimes sounds contrary, but you don't want to be the best ground because that's where all the stuff, all the current will go. But yeah, you would bond to those rather than put your own ground in.
Interesting. Okay, yeah, that makes sense. All right, here's another one. To test the ground at the tower with each leg attached to the ground ring, is it okay to use the 3/4 probe tester?
It is. You have to understand what's what, but I'm assuming you mean 3 or 4 stakes, like the fall of potential method, and it is. You have to know. You have to have a rough idea of how far apart the ground rods are, so you know how far to run out those probes. But again, most fall of potential testers these days will tell you if you're not far enough. So yeah, that's the test method that I said was much more time consuming than the clamp-on tester. That's how I said we used to even test poles.
Okay, great. Thank you very much. Let's see here. Here's another one. On a tower or building ground ring, I need to get below the ring to eliminate wire continuity by attaching to the lateral lead to the ground rod or at the ground rod top if pad welded to the ring, correct? Did you get that? It's question number 10, if you can read it on our screen here. Tower or building ground ring. Did that make sense, Ed? I wonder if I'm having trouble hearing here. My connectivity is not. Okay. So Ed must, there might be something. Ed might be having some issues. I did have a comment from you, Michael, saying it's an ART method question. So perhaps we can get back to that person. Or do you want to handle that?
But a ground tester that facilitates the ART method or the attached rod technique